Okay, so get this. We're diving into the world of unhackable internet today.
No, seriously.
You guys have sent in a bunch of articles about a quantum encryption breakthrough
Yeah.
that uses light and color to protect data.
Really wild stuff.
And honestly, it sounds like straight up sci-fi.
It does.
But it's Real Deal Holyfield, and we've got expert speaker here
Hey!
to break it down for us.
You know what's so fascinating about this is
What?
we're not just talking about like making our current security a bit better.
Okay.
This could completely change the game.
Really?
Yeah, we're talking quantum mechanics here.
Okay.
The rules that govern the tiniest particles in the universe.
Yeah.
And those rules, they're totally different than anything we experience
Interesting.
in our regular world.
Okay, so before we get lost in the quantum weeds, I think we need to figure out why this is such a big deal.
Yeah.
You mentioned quantum computers earlier, so paint a picture for us.
Uh-huh.
What kind of threat do these things pose to our online security,
Well,
like as we know it?
think about it this way. Everything you do online, your banking, your shopping, your private messages, it's all protected by encryption, right? That encryption is based on math problems.
Yeah.
That would take regular computers years, even centuries to crack.
Wow.
But quantum computers are different.
Okay.
They use these things called qubits,
Okay.
which can be both a 1 and a 0 at the same time.
How is that even possible?
It's thanks to this thing called superposition.
Superposition.
Yeah, it's basically like having a computer
Yeah.
that can explore every possible answer to a math problem
At the same time.
simultaneously.
So they're like superpowered code breakers.
Exactly.
Yeah.
And that's a huge problem for our current encryption methods.
Okay.
A quantum computer with just a few hundred qubits
Yeah.
could crack the 256-bit encryption that protects most of our online world
In how long?
in a matter of hours or even minutes.
Are you serious?
I know one of the articles you sent mentioned how worried cybersecurity experts are. Yeah.
About this, especially when it comes to like government secrets or financial data.
So someone could steal my encrypted data today,
Potentially.
just sit on it, and then wait until a powerful enough quantum computer comes along to unlock it all.
It's a scary thought.
It is. Like harvest now, decrypts later.
That's exactly the threat we're facing.
That's unsettling.
And it's why this research into quantum encryption
Yeah.
is so important, especially this new breakthrough using light and color.
Okay, so quantum encryption, how does that actually work?
Sure.
What makes it so much more secure than what we have now?
Well, think of it this way. Our current encryption methods are like building a really tall, really thick wall
Okay.
to protect our data.
Yeah.
It's effective for now, but a quantum computer is like having a battering ram
Oh, no.
that can eventually smash through any wall.
Okay.
Quantum encryption, on the other hand, is like building a wall that's invisible and constantly shifting, making it nearly impossible to even find, let alone break through. So you're saying it's not relying on math that can be cracked.
Nope.
It's using the laws of physics themselves as its defense.
Exactly.
Okay, the laws of physics. Now I really feel like I'm about to enter the twilight zone.
It is pretty mind-bending stuff.
Can you give an example? How does physics actually protect data?
Okay, so let's say someone tries to intercept a message that's been encoded using quantum encryption.
Okay.
At the quantum level, just trying to eavesdrop, just the act of observing, actually changes the message itself.
What?
It's like trying to sneak a peek at a letter someone is writing, but just by looking at it, you smudge the ink and alert the writer that someone's snooping.
So in this case, both the sender and the receiver would know immediately that someone tried to intercept the message.
Exactly. And that's a huge advantage of quantum encryption. Any attempt to tamper with the data is instantly detectable.
So it's like a built-in alarm system that goes off the moment someone tries to peek at your secrets?
Exactly.
Okay, I'm starting to see why this is such a game changer, but I gotta ask.
Yeah.
Where does the light and color part come in?
Right.
It just seems so artistic for something so high-tech.
It is really cool.
Yeah.
So light is made up of these tiny particles called photons.
Photons?
Yeah, and photons can exist in different states, including different colors, which represent different frequencies.
Okay.
And what these researchers have figured out is how to use not just the color of the photon, but also its spatial property.
Spatial properties.
Like how it's moving the direction it's spinning to encode information.
So it's not just like shining a red light for 1 and a blue light for 0. Nope. There's more to it.
Way more.
Oh, okay.
Imagine sending a message.
Yeah.
Not just by changing the color of a light bulb, but by making the light beam twist or spiral in a specific way.
Really?
It's a simplification,
Okay.
but it gives you an idea of the added complexity.
Why?
It's like creating a secret code that's hidden within the very fabric of light itself.
Okay, now we're talking a multi-dimensional code hidden in light. And any attempt to mess with it triggers an alarm.
That's right.
This unhackable internet is starting to sound like a real possibility.
It is.
But how do we even control light at that level?
Right.
Is that even possible outside a lab?
So that's where we have to get into two of the most mind-blowing concepts in quantum mechanics.
Hit me with it.
Superposition and entanglement.
Superposition and entanglement.
And yes, believe it or not, they've figured out how to do this outside the lab.
Okay. I am officially ready to have my mind blown.
Yeah.
What are superposition and entanglement?
Okay.
And how do they play into all of this?
Imagine flipping a coin until it lands its both heads and tails at the same time, right?
Yeah.
That's kind of like superposition.
Yeah, okay.
A photon can be in multiple states.
Okay.
Multiple colors in our case.
Yeah.
All at once. That's how they can carry so much more information than a regular bit.
So instead of just being red or blue, one photon could be red and blue and green and yellow.
You got it.
All at the same time.
All at the same time.
Okay, that's crazy.
Now for entanglement, this is where things get really wild.
Okay.
Okay. Think about having two gloves from a pair,
Yeah.
but they're in separate boxes. You open one box and you find a left-handed glove.
Yeah.
Instantly. You know, the other glove must be right-handed.
Right.
Even though you haven't even looked in that box yet.
They're connected even when they're apart.
Exactly.
That is wild.
Entanglement means two particles are linked. If you change something about one of them, the other one changes instantaneously, even if they're miles apart.
No way.
It's this spooky connection
That's crazy.
that allows for incredibly secure communication.
So we're talking photons that can be multiple colors at once because of superposition.
Yep.
And then we're entangling them. So that messing with one instantly affects the other, alerting everyone that something's wrong. Okay, it's starting to come together in my mind.
Good.
But there's got to be more to it, right?
There is one more piece of this puzzle.
Lay it on me.
It's a principle that's just as important as superposition and entanglement.
Okay.
It's called the no cloning theorem.
The no cloning theorem.
You know, this one is especially relevant to some of the concerns you brought up in your notes about data breaches.
Oh, interesting. Okay.
The no cloning theorem basically says that you can't make a perfect copy of a quantum state.
So if someone tries to intercept a message encoded in entangled photons,
the
very act of trying to copy it would introduce errors, immediately revealing that someone's trying to eavesdrop.
Exactly.
It'd be like trying to photocopy a one-of-a-kind painting.
Yeah.
The copy would always be flawed, and everyone would know it's a fake.
A good analogy.
Okay, I think I'm starting to wrap my head around this.
Awesome.
We've got photons that can be in multiple states at once.
Yep.
We're entangling them. And then we have this no cloning theorem that prevents anyone from making a perfect copy.
That's right.
This is a lot to take in, but I see how these principles combine to make quantum encryption so secure.
It's pretty amazing stuff.
But is this just a theory?
That's the really exciting part.
What?
It's not just theoretical anymore.
Really?
Scientists have actually built systems that use this light and color method of quantum encryption.
No way.
And get this, they're using the same fiber optic cables.
Really?
That we use for the regular internet.
Oh, wait, seriously, they're sending these quantum encrypted messages through the same cables that bring Netflix to my house.
It's pretty wild, right?
That's mind-blowing. Tell me more.
It's amazing. It means that this technology isn't some far-off sci-fi dream.
Yeah.
It has the potential to be integrated into our existing infrastructure.
Right.
Which makes it much more practical and cost-effective.
Than other quantum communication methods.
Yeah.
Okay. I am officially hooked. This is way more interesting than I ever imagined. So what kind of results are we talking about?
Yeah.
How far along are we on this journey to a truly unhackable internet?
Well, that's what we'll dive into next.
Okay.
Get ready, because the details of these experiments are even more mind-blowing than you might think.
All right, bring it on.
All right.
I'm ready for more.
Okay.
Okay. We're back, and I am still reeling from that last revelation.
I bet.
We're talking about sending unhackable messages
Yeah.
through the same fiber optic cables I use to stream cat videos.
Pretty amazing.
It's mind-boggling.
It is.
So tell me more about these experiments.
Right.
How are they actually doing this?
So picture this, a high-tech physics lab.
Okay.
All sleek and shiny with lasers and mirrors and all sorts of sensitive equipment humming away.
It's a far cry from cat videos.
It is.
So where do the photons come in?
Right.
Are they beaming them across the room or something?
Pretty much at the heart of it all is a laser.
Yeah.
But not just any laser.
No, yeah.
It has to be extremely precise, emitting photons that are all perfectly in sync with each other.
I see.
Think of it like a perfectly choreographed dance troupe.
Okay.
Every photon moving in perfect unison.
Okay. I'm picturing it a laser ballet.
I like it.
So this laser is generating the photons that are going to carry the quantum information.
You got it.
Okay. And then?
Then they use a special device called a modulator.
A modulator.
To control the properties of those photons.
Okay.
It's like a control panel for light.
Wow.
Allowing them to fine-tune the frequency and phase of each photon.
Hold on, back up a second.
Yeah.
We talked about frequency before, the color of the light.
Right.
But what is phase?
Okay, so you know how waves can have different shapes?
Yeah, like ocean waves?
Exactly. Some are gentle and rolling, while others are tall and choppy.
Right.
That's kind of like the phase of a light wave.
Okay.
It describes the position of a point on that wave relative to a fixed reference point. And just like we can encode information by changing the color of light, we can also do it by tweaking its phase.
Okay, so we've got color and wave shape.
Yep.
But what are they actually doing to these photons?
Yeah.
How are they physically encoding the message?
It's a bit like imprinting a secret code on each photon.
Okay.
By adjusting the frequency, they can write information onto the photon using different colors as a code.
Okay.
And by manipulating the phase, they're adding another layer of complexity.
So it's like
by adding a secret handshake to the color code.
Okay, I get it. So it's not just a simple on-off switch like a regular bit.
Yep.
We're talking about encoding information in multiple ways.
That's right.
Within a single photon.
Exactly. It's what makes this type of quantum encryption so secure.
Right, because cracking the code would require knowing not just the color of the photon, but also the specific details of its wave shape.
Exactly.
Got it. So we've got our laser-generated, color-coded, wave-shaped photons ready to go.
Oh, okay.
What happens next?
So from there, they send these super secret photons on a journey. Through a transmission channel.
A transmission channel.
Now, this channel could be a fiber optic cable, just like the ones that bring internet to your home.
Yeah.
Or in some cases, they're even experimenting with sending them through the air.
Through the air.
That's called free space quantum communication.
Wait, sending photons through the air?
Uh-huh.
Isn't that like a million times harder?
It definitely has its challenges.
Yeah, I feel like there's a lot more that could go wrong.
When you're sending photons through the air, you have to contend with all sorts of environmental factors.
Like what?
From weather conditions to background radiation, all of which can disrupt the delicate quantum states.
I see.
But researchers are making progress in this area because it opens up some amazing possibilities.
Like what?
Well, for one, free space, communication would allow us to send quantum encrypted messages to satellites.
Wow.
Which could then relay those messages anywhere in the world. We could even potentially use it to establish secure communication links between different countries without relying on any physical infrastructure on the ground.
Satellite-based quantum internet.
It's a possibility.
Sign me up.
Right.
But let's say we stick with fiber optics for now.
Okay.
Our photons are zipping through the cable.
Yeah.
Carrying their secret messages.
Right.
How does the receiver on the other end actually read the message?
Good question.
I mean, how do you even see the color and wave shape of a single photon?
So that's where they use highly sensitive detectors that can capture individual photons and analyze their properties.
So they can tell you the color of a photon and the wave shape.
These detectors can tell you not only what color a photon is, but also its phase, its polarization, and other characteristics.
So they're not just picking up on a flash of red or blue light. They're actually measuring all the subtle details of each photon's wave to decode the message. It's like having microscopic eyes that can see the secrets hidden within each particle of light.
A great way to put it.
But it's not always perfect.
Right.
Things can go wrong in transmission. Like a photon could get lost.
Yeah.
Or its properties could be disrupted by noise in the channel.
Exactly. And that's why they've developed something called quantum error correction.
Quantum error correction.
It's a whole area of research dedicated to protecting quantum information from noise and errors.
Okay, so even if some of the photons get lost or scrambled along the way, the message can still get through.
That's the goal. And remember, we're talking about the very early stages of development here.
Right.
Researchers are making incredible progress in understanding and mitigating these errors.
Okay, so they've got this incredible system. Generating, modulating, transmitting, detecting, and even correcting errors in these light-encoded messages.
It's amazing stuff.
But how well does it actually work?
Well, that's what's so exciting. They've already managed to transmit quantum keys.
Okay.
Those are essential for secure communication.
Yeah.
Over distances of up to 50 kilometers.
50 kilometers.
Using fiber optic cable.
Through a cable.
And when it comes to free space transmission, they've even managed to send quantum encrypted messages to a satellite orbiting hundreds of kilometers above the Earth.
Wow. 50 kilometers through a cable and hundreds of kilometers through the air.
Pretty impressive, right?
That's really impressive. But is that far enough to be practical?
That's a good question.
I mean, for a truly global quantum internet, we need to be thinking much bigger.
You're right. 50 kilometers is just a start for a truly global quantum internet. We'll need to find ways to extend the reach of these quantum signals significantly.
Okay.
But that's just one of the many challenges that researchers are working on.
Co-challenges.
Yeah.
I have a feeling this is where things get really interesting.
It is.
What are some of the biggest hurdles standing in the way of this unhackable quantum internet?
Well, there are a few big ones, and they're not all technical.
Okay, lay it on me.
But we'll dive into all of that after the break. Stay tuned, because the future of the internet might be more mind-blowing than we can even imagine right now.
All right, we're back, and I'm ready to tackle those challenges you mentioned.
Okay.
We've talked about the amazing potential of quantum encryption.
It is pretty amazing.
Sending these unhackable messages through light and color.
Right.
Even beaming them to satellites.
Yeah.
But let's be real. There's got to be some hurdles on the road to this quantum internet utopia. Right?
Yeah, there are definitely challenges, and they're not all easy to solve.
Give me the rundown. What's the biggest technical challenge?
One of the trickiest is maintaining quantum coherence over long distances.
Right, because we're talking about incredibly fragile quantum states.
Exactly. Things like temperature changes, vibrations, even stray photons can disrupt those entangled photons and cause errors in the transmission.
So it's like trying to carry a bubble across a crowded room?
It's a good analogy.
Without it pumping.
Yeah, and the further you try to send those photons, the more likely they are to bump into something and disrupt the whole message.
So what's the solution?
Well, one promising area of research is the development of quantum repeaters.
Quantum repeaters.
Think of them as specialized relay stations.
Okay.
Placed along the fiber optic network.
Like rest stops for weary photons.
Exactly. These repeaters would be able to amplify and refresh the quantum signal, correcting any errors and extending the range of quantum communication.
So even if some photons get lost or scrambled along the way, the message can still get through.
That's the idea. It's like having a chain of runners in a relay race, each one carrying the baton for a short distance before passing it on to the next.
Okay, that makes sense. Quantum repeaters check. What other challenges are we up against?
Another big one is integration right now. Quantum communication mostly happens in highly specialized labs with very expensive and complex equipment. But a truly unhackable internet can't just exist in a few research facilities.
Right. It's not like we're going to rip out all the cables and start over.
Exactly. So we need to find a way to make this technology compatible with the existing infrastructure of the internet.
So how do we bridge that gap?
Well, one approach is to develop hybrid systems that can handle both classical and quantum communication.
So some data speaking the language of quantum mechanics. And other data sticking with the old school bits and bytes.
It's a good analogy. And then there's the development of quantum compatible hardware and software. Imagine routers and servers that can speak both quantum and classical, seamlessly integrating quantum communication into the existing network. It's a huge undertaking.
It sounds like it, but I guess that's what makes it so exciting.
It is.
We're talking about fundamentally changing the way the internet works.
That's right.
Making it inherently more secure by harnessing the power of quantum mechanics.
Exactly.
You said there were some philosophical challenges as well.
Right. One that's been getting a lot of attention is the potential for a quantum divide.
Quantum divide? What's that?
Well, right now, this technology is still in its early stages. and access to it is limited to certain countries and organizations with the resources to invest in research and development.
Okay.
But what happens when this technology becomes more widespread?
You're talking about a world where some people have access to unhackable communication, while others are left vulnerable.
Exactly. And that raises some serious questions about equity and access. Who gets to benefit from this technology? How do we ensure that quantum encryption doesn't just create new forms of inequality? These are things we need to think about carefully as we move forward.
It's a good point. And I imagine there are some ethical considerations as well, right?
Definitely.
I mean, a truly unhackable internet, that's a powerful tool.
It is.
Could it be misused?
It's definitely something we need to consider. While quantum encryption offers unprecedented security, it also raises questions about privacy and accountability.
Like how?
For example, if communication is truly unhackable, could this make it easier for criminals to operate without detection?
That's a scary thought.
Or what about situations where law enforcement needs to access information for an investigation? These are complex issues with no easy answers.
It sounds like this technology has the potential to change not just the internet, but society as a whole.
It does, and it's crucial to have these conversations now, while the technology is still in its early stages of development. We need to think about the potential consequences, both positive and negative, and work together to shape the future of quantum communication in a way that benefits everyone.
So we've got technical challenges, infrastructure challenges.
Yeah.
And some pretty weighty ethical and societal questions to grapple with.
It's a lot.
With all of that on the table, is it even realistic to think that we can actually build a truly unhackable internet?
I absolutely believe it's worth it. Think about it. Everything we do online, from banking and shopping to communicating with friends and family, relies on the security of the internet as quantum computers become more powerful. That security is increasingly at risk. Quantum encryption isn't just a cool idea, it's a necessary step to protect ourselves in a rapidly evolving digital landscape.
It's like building a stronger lock on our digital doors.
Exactly.
Before the quantum thieves figure out how to break in.
And beyond security, the possibilities are truly exciting. Imagine instantaneous, secure communication across vast distances, the ability to collaborate and share information in ways we can't even fathom right now. Quantum encryption has the potential to revolutionize not just the internet, but also fields like medicine, finance, and even space exploration.
Okay, I'm convinced. Sign me up for the quantum internet revolution.
Yeah.
But realistically, when can we expect to see this become a part of our everyday lives? Are we talking years, decades, centuries?
It's hard to give an exact timeline, but the research is moving at an incredible pace. We're seeing breakthroughs all the time, and many experts believe that some form of quantum communication will be commercially available within the next decade or two.
So, not quite ready to ditch my VPN just yet.
Not yet.
But the future's looking bright and unhackable.
Exactly, and that's what's so exciting. We're on the verge of a new era of communication, one that leverages the fundamental laws of the universe to create a more secure and connected world.
Well, there you have it, folks. A deep dive into the incredible mind-bending world of quantum encryption. It's a complex and rapidly evolving field. But one thing is clear, the future of the internet might be more secure, more connected, and more mind-blowing than we ever imagined.
And as we move forward, it's important to stay informed, ask questions, and engage in the conversation about how we want to shape this quantum future.
So to our listeners out there, we leave you with this. What are your thoughts on all of this? Does the idea of an unhackable internet excite you, scare you, or maybe a little bit of both? Let us know. Until next time, keep exploring, keep those sources coming, and we'll catch you on the next Deep Dive.